Great. Great. Well, thank you so much, Josh. I think we're ready to get started, and this is a really a fun webinar for everyone. I'm Kai Gray. I'm the host, and literally we'll just be introducing the panel. We'll hear two presentations. One at the on Firecracker and Liquid Metal. It's a very interesting topic, especially for folks of you like myself who are sort of a bare metal head. And doing interesting things on bare metal, which is very near and dear to my heart. I love this stuff, and what AWS and Weaveworks are working on is very cool. So I'm excited about this. So what we're going to hear is a presentation. Samartha, if you would like to introduce yourself, I will torture your last name, and I apologize. But Samartha, Richard Case, Chris Lavery will be presenting, and we'll hear sort of an overview of Firecracker. Sorry if I called it Fireworks earlier. Firecracker, and then a really interesting use case. So, without further ado, let me introduce Samartha. And if you want to take it away and share your screen, that'd be great.
Thank you so much, Kai, and thank you so much, Josh, for this forum. Without further ado, I'm going to get started and share out my screen. If you can just give me a thumbs up that you can see my screen, right?
Yep.
All right, fantastic. So hello, folks. My name is Samartha Chandrasekhar. I'm a product manager in Amazon Web Services. My work has largely been focused on the compute parts of AWS in the form factor of virtual machines as well as containers. I'm currently the product lead for Firecracker. In the past, I've been involved with various other projects within EC2, within the container space, such as Bottle Rocket, etc. I'm excited to talk about Firecracker and share details about it with you all today, and also set the stage for a subsequent presentation by our friends at Weaveworks. To get started, in terms of what is Firecracker, this really is an open source virtualization software that is purpose-built from the ground up for the purposes of creating multi-tenant services for things such as container hosting or hosting function as a service type of workloads. They're best represented by things or by AWS services that you can use, such as AWS Fargate, which is essentially a serverless container offering, and AWS Lambda, which is a function as a service offering. And going forward, we're using Firecracker for other services and other use cases as well. Now, if you look at both Fargate and Lambda, or function as a service and container as a service, essentially there are certain key tenets associated with with these services. The first one is that because it's a cloud service, it has to be multi-tenant from a security perspective, from a resource isolation perspective, etc. The second part is there's an expectation of an instant on experience from our customers. In the container world, there's an expectation that containers typically come up instantly, and even more so in a function as a service world. And that's where Firecracker comes to play a role. Firecracker today is used in production across both Fargate and Lambda, and is soon going to be the basis for other upcoming services as well. Firecracker also forms the backbone for another service called App Runner, which uses Fargate behind the scenes. In terms of properties of Firecracker that lends itself to building some of these services, it is the three that you see here. The first one is, again, it provides multi-tenant security and resource isolation across its artifacts that we call micro VMs, and I'll get into that in some detail in due course. The other part of it, which is very important, is a rapid startup experience that really is the basis for some of these instant on type of customer experiences. And the third and very important part is cost efficiency. Oversubscription of resources is a key tenet for Firecracker, and it's one of the things that we can use to ensure high cost efficiency. The other part of it is that it is minimalist in design from the ground up, and that certainly also helps with sort of managing resource usage, reducing security attack surface, and so on. To talk about Firecracker and sort of what it can unlock, I want to do that with an example and a use case. And the use case that I'm going to choose today is Fargate. There's plenty of material out there around how Firecracker is used with Lambda, not as much around Fargate. So I thought I'd focus on Fargate and sort of look at Firecracker from the lens of how it's able to enable Fargate and sort of the value proposition of Fargate. And before getting started, I just want to set some context on what Fargate is and what it does for customers. So Fargate, if you aren't aware already, is essentially a serverless container offering, in the sense that if you want to run containers, that becomes the modality for interaction as opposed to virtual machines, etc. Prior to Fargate, the workflow to run containers on AWS or in most other places looked something like this, which is that you would first spin up EC2 virtual machines that we call instances as your unit of capacity, and then install certain software inside these instances that supported containers. It could be a machine image that already came with a container runtime, such as Podman or Containerd or Docker, etc. And you'd also install agents needed for container orchestration, be it a kubelet or an ECS agent or its equivalent in Mesos or whatever else. And then your environment would be sufficiently ready to run containers. And then you would, again, you would be able to schedule these containers inside of these running instances that you spun up. Also, the act of keeping the software stack needed to run containers inside these virtual machines would be the customer's responsibility. And this includes things like functionality updates, security patches, etc., on an ongoing basis. One of the things that Fargate did was sort of make it super simple. So this is a high-level view of how Fargate works, which is that the interaction model is that you provide to Fargate a collection of containers that you want to run, either wrapped up as a Kubernetes pod or as an ECS task. ECS, by the way, is a homegrown container orchestrator at AWS. And a task is essentially a collection of containers. And you come to Fargate and say, here are these containers, run them for me. And you can interact at the modality of the container or sort of the wrapper around them, such as a task or a pod, as opposed to having to deal with virtual machines, capacity, keeping these virtual machines patched and up to date, etc. And thus it greatly simplifies the experience of running containers. And it has unblocked and sort of enabled a lot of customers that were previously sold on the value proposition of containers regarding their portability, regarding sort of their startup time, etc., to actually move to using this technology in a meaningful way in the cloud. Now, there are two challenges for Fargate in terms of sort of realizing some of these value propositions for Fargate. The first one is that at AWS, we only trust the virtualization boundary or the VM boundary for multi-tenant security and resource isolation. We do not trust a shared kernel. Now, if you look at how the container space evolved with Docker and many other companies in that, and many other stakeholders and participants, it really was a layer of software on top of kernel primitives. So today, a container, for all practical purposes, is essentially an artifact that uses Linux kernel primitives such as C groups, such as kernel namespaces, such as seccomp, for the purposes of security and resource isolation. And similarly, in the Windows world, there are equivalents of that. There's Windows kernel job objects, etc. But essentially, it is just kernel isolation. At AWS, based on our track record of operating services like EC2, based on what we've seen, also based on sort of the track record for CVEs, which are vulnerabilities and exposures at the syscall level, and just by looking at the number of CVEs that are found and fixed on an ongoing basis, we came to the conclusion that the shared kernel isolation boundary that is sort of native to containers with C groups and kernel namespaces and seccomp doesn't meet our needs for multi-tenant isolation for running workloads in the cloud. And this includes both security isolation and resource isolation. And the other challenge here is that with the container ecosystem, customers have an expectation around an instant on experience, which isn't necessarily the case with virtual machines, which take their own sweet time to spin up. Again, we've constantly been improving our VM launch times, but they're nowhere close to sort of the expectation that customers have with regard to instant on with containers or with things like Lambda functions. And so these were foundational challenges, which is that, on one end, you had kernel isolation primitives that provided the right level of startup time and sort of and resource sharing, while at the same point in time, they just didn't meet the cut for our security bar. And on the other hand, you have VMs that certainly meet the needs of our security isolation bar, but are just not sufficiently fast enough to provide an instant on experience. So there was a foundational challenge here for Fargate. So one of the solutions. Sorry,
can I just ask you a very quick question about that? If I'm curious, where do you think the customers got this expectation on the this sort of sub 1 second start time?
I think it largely evolved based on sort of how containers came to be, which is that if you look at Docker, when they sort of democratized containers as a result of their work, it was a layer of software that was built on top of kernel isolation primitives. And when you spin up a Docker container, either in a VM or in the cloud or on a local laptop, it comes up like that. And that's how. And that was how the expectation was set. Since you started from a pretty fast place, because essentially a container is essentially a Linux process which is protected by a bunch of kernel primitives, and these things start quickly. So that's where it started. They didn't start from VMs, and so that's at least my view on how that expectation is set.
Thank you.
So since we had to balance these two needs when we first started Fargate, the solution that we came up with was something that we call EC2 warm pools that has now been productized, and it's a feature of auto scaling groups, etc. But essentially, what we do here is that we pre-start a collection of EC2 virtual machines that we call instances, and keep them running. And every time a customer brings a container or collection of containers and says, run this for me, we go ahead and schedule that in one of these instances that we pull out of a warm pool. And then once those containers sort of cease to run, then then we return back to that instance to the warm pool after doing some amount of scrubbing and things like that make it suitable for reuse. Now, this certainly is a solution that helps address both the security isolation needs as well as the startup time needs, because we're scheduling customer workloads in virtual machines that meet our security bar, while at the same point in time there is no waiting for a VM to spin up from scratch, because we're not talking about cold starts of virtual machines here. We're talking about sort of running virtual machines that are into which resources are already scheduled. While this certainly met sort of the functional needs, there are certainly challenges here, and there are lots of downsides that make it unviable for the longer term. And the primary one is around sort of warm pool capacity management. So typically, to ensure a good customer experience, we size these warm pools to be something that is representative of peak customer demand that we see. And if you look at some of these container workloads or these function type of workloads, it is really swarms of ephemeral workers that come and go pretty quickly in very large numbers. And thus it's very hard to model them, and there is very little advance notice that we have. And so invariably what ended up happening was that we had a large capacity or a large sort of fleet of running EC2 instances as a part of these warm pools that were very poorly utilized. It was only a subset of these instances that were utilized, and the rest was all essentially cost that we had to eat. These were sort of VMs doing no useful work, but they represented capacity that effectively a service like Lambda or Fargate is paying for, either directly or indirectly, because this represents capacity that we could sell to other customers. And so that was the downside that made this model very challenging to work with from a longer term perspective, and sort of at scale, some of these costs add up really quickly, and it can be, end up being a very large dollar amount. So that's when Firecracker came to the rescue. This multi-tenant solution that provides fast startup time, really came to the rescue and sort of helped us achieve all of what we were looking for, which is the right level of security isolation, the right level of startup times, as well as at a price point with cost efficiency that made it viable to run a business with our function as a service or as our container as a service offering. And really, if you look at the internals of Firecracker, the reason this is viable is because we built this from the ground up. Sort of almost as a history lesson, how we started with Firecracker was that we forked an existing open source project that was called CrossVM, which is short for Chrome OS Virtual Machine, that was put out in the public domain. The use case for CrossVM was very different in terms of application isolation on Chromebooks and devices like that. It has sort of, since we forked it, it has sort of evolved in drastic ways to the point where there's very little similarity with regard to use case or with regard to how things have evolved with respect to CrossVM. But that's how Firecracker started. And the reason Firecracker is able to work here is because if you take a step back and look at virtualization, there are really two parts here. Part one is sort of using hardware virtualization extensions to create these isolated and secure partitions that are typically known as virtual machines. So using extensions like VTD or VTX primarily and VTD, we're able to create hypervisor partitions that provide the right level of security and resource isolation using essentially hardware extensions. And at the same, and the second part to virtualization is really around device emulation. Typically, when you think of a virtual machine, it is for all practical purposes, a software emulated version of a physical machine. And a physical machine typically follows a certain specification that is usually compliant with or a variant of an IBM spec from 1984 that's called PC80, and that's how sort of the name PC comes. And this specification mandated sort of things like a BIOS. Every physical server ought to have a BIOS, a PS2 mouse, a PS2 keyboard, a floppy disk controller, and so on. And in most cases, in virtual machines that are in the cloud or on premises on VMware or on Hyper-V or on-prem or something like that, all of these devices are emulated. So there is the hypervisor partition that provides security and resource isolation. And then there is sort of device emulation for the sole purpose of compatibility and compliance against a specific standard. Now, when we looked at sort of these modern day workloads that we were looking to run in terms of containers or functions, the odds that they depended on like a PS2 mouse or a floppy disk controller was like super minimal. So one of the things that we were able to do is we were able to look at the list of devices that are being emulated and then pare that down to an absolute bare minimal subset. And as a result of doing that, we were able to essentially reduce the resource overhead as well as startup time drastically. Because when we looked at where the time went when it comes to why virtual machines are as slow as they are, a large part of it was around device emulation and sort of going through all of these code paths, both at the hypervisor level as well as in the OS level that's running inside of the guest to initialize sort of things that are related to mouses and keyboards and or mice and keyboards and floppy disk controllers and things like that, which is unneeded parts. So essentially,
so what you're trying to tell us is that AWS is not running a fleet of floppy disk bound machines.
Well, we no longer are with Firecracker
Yeah,
for
good.
Fargate and Lambda, which is comforting to know. But in the case of EC2, yes, I mean there is sort of all of that device emulation. Now we do a lot of interesting things with EC2 in terms of offloading all of that emulation away from sort of the physical server onto a separate offload card. As a part of our Nitro system, but that's a separate story and perhaps the subject of another talk that I'm happy to do. But
that sounds great.
In the case of Firecracker, the reason we're able to sort of get the best of both worlds, which is VM isolation for security as well as fast startup, is because we preserve all of that VTX and VTD usage for creating those hypervisor partitions. But at the same point in time, we emulate only a small subset of devices. And thus we've created this artifact that we call a micro virtual machine. That's not a full virtual machine. And this is particularly well suited for these modern workloads like functions and containers and so on. And so that really is sort of the basis for Firecracker in terms of how we started out. It started from an evaluation of why do virtual machines take as long as they do for the purposes of boot up and sort of eliminating the unneeded emulated software. There
That's
are a few.
So I just there was a question in the QA box. Venkat, do you want to would you like to ask that question? And Josh can he? There.
Yeah.
Hey,
It'll be my pleasure. It'll be my pleasure. Thanks for the opportunity.
Thanks.
Chandrasekhar, thanks for a great enlightenment that is going on. And I just was wondering if there is any thing with respect to a sort of performance matrix that is handy available to you. Is there anything that you could share with us or something of that nature? That is one thing.
No, good point. We certainly, at least right now as we speak, we don't have a white paper or sort of an official performance comparison per se, but there are plenty of folks that have done it for the purposes of both, academic papers that are out in the public domain around Firecracker, as well as benchmarking to sort of choose a solution for their specific needs, and really, performance has not been a concern at all, at least from a compute perspective. There is of course, if you benchmark it against EC2, where we do a bunch of things to offload certain functions around storage and networking and device emulation to a specific offload card. For IO bound workloads, it is likely not as competitive as EC2 is, and again, EC2 comes with a diversity of instance flavors. So if you're looking at sort of the top end for IO performance to run like a database or something like that, then this is probably not in the same envelope. But for the purposes of just compute performance, there is no concern. And the fact that we've removed so much emulated software means that performance, at least if you look at performance from the perspective of startup times for these micro VMs, it is best in class. If you look at performance from a resource overhead perspective, it is best in class. If you look at guest performance from sort of the number of IOPS you can drive inside of a micro VM, I think you might do better with like an EC2 instance that is optimized for that workload, where we're able to offload some of these IO functions to specific accelerated hardware and things like that.
If I'm not becoming a showstopper, there one or two more. Do you mind if I just request you to enlighten me? Or I can wait for it.
Yeah. I was just going to ask it. We love the participation, so this is great. Why don't we at the end we'll have a Q&A section?
Yes.
Would it be okay with you if we just did that there? And then I just want to, it's about 12:30. I want to be sort of respectful of the time. If you want to continue the presentation, and we'll get to all these questions, that's great.
Certainly. So the other thing that I wanted to do before I wrap up was compare what sort of the data plane looks like for a service like Fargate with the previous model, which is with EC2 warm pools, and then contrast that with what it looks like with Firecracker. And then there's also this integration point with Containerd, which is a container runtime that I want to briefly touch upon. So this is sort of a view of what the data plane looks like for Fargate with EC2, where essentially, as you might be familiar, sort of anything below the, or anything to do with virtualization and capacity is managed by AWS and EC2. And now Fargate shifts our shared responsibility model to be above the container runtime. But here, what you see is essentially an EC2 instance that is managed by Fargate, and you see a network attachment, a network interface that is owned by a Fargate account that is attached to this instance that is hosting customer containers. Of course, the customers can attach their own networking interfaces for the purposes of other networking operations, but for control plane integrations and interactions, there is a networking interface here, and the stack also looks pretty straightforward in the sense that this is there is sort of this is the view of a VM running on a hypervisor, and then there is a kernel, there is a container runtime, there's also an agent that's needed for control plane interactions, and then in user space there are customers containers that are running that are either packaged as a task, which is an ECS construct, or as a pod, which is a Kubernetes construct. Now with Firecracker, if you contrast that, it looks slightly different. Now, because Firecracker is a virtualization software here, it requires access to hardware virtualization extensions, which are currently available only with with an instance offering that we call bare metal instances that come with a .metal extension. And so that's where we run our Firecracker fleet. And so on top of that EC2 bare metal offering, there is a Firecracker virtualization software, the VMM, and then there is the agent, just like you saw for Fargate, and then there is also this layer that's called Firecracker Containerd, and I'll get to that in due course, and I'll try and be brief here. And then on top of that is sort of what runs inside of the VM, or the micro VM in this case, which is the guest kernel as well as customer containers, as well as there's a shim to talk to Containerd. Now, one of the important things that we've done with Firecracker for the purposes of Fargate is that in the previous world, if I can quickly go back to the previous slide, there is one container runtime, or one instance of the container runtime, which can be Docker or Containerd in our case, per VM that is hosting customer containers. In the case of Firecracker, there is one instance of Containerd that is sort of modified to work with Firecracker that is one per virtualization host as opposed to one per micro VM. And through this model, we are able to get lots of savings from a resource usage perspective, because there is very little duplication here. We don't have an instance of that same agent running in each micro VM. Also, if you from a security attack surface perspective, in a hypothetical case, in a warm pool, if there is a container breakout to the host, then there is the ability to access these ENI interfaces. Here, a breakout is contained inside of the micro VM, so there's the virtualization boundary that's protecting things, and also the ENI that allows sort of Fargate control plane interaction is attached at a level that is below the micro VM, and so there are sort of dual benefits there. The key takeaway here, of course, is if you didn't follow much of this, is that one of the things that we've also done is improve the integration of Containerd, which is typically the container runtime, with Firecracker, and we call this Firecracker Containerd. And we've also done this in a manner that tries to improve resource usage as well as security attack surface for deployments like Fargate or similar such deployments that you can have as well.
But before we move on, can I just there's a question that came in, and I think it'd be great to respond to this, and then probably a good time to move on to the use case. I'm not sure how many more slides you have, but let's go to this question very quickly. And the question is, do we have a project that replaces pod with Fargate VM?
Sorry, Firecracker VM.
Oh, with Firecracker VM, yes.
So say the question one more time.
So do we have a project that replaces a pod, like a Kubernetes pod, with a Firecracker VM?
So in this case, I'm not sure I follow that question, because what we're doing in this case is we're essentially running the Kubernetes pod inside of the Firecracker micro VM. So pod is a collection of containers, and that collection of containers is run inside of a single micro VM. So we're not looking to replace the pod itself. We think the pod is a very powerful abstraction that has wide acceptance and integration with the rest of the ecosystem. It is about, if you provide us a pod, how do we run it? Or sort of, if you realize a solution with, say, Weave Firecube, a pod is essentially run inside of a micro VM. So it's more of a holding abstraction rather than one that we're looking to to replace the pod with.
Okay,
Great.
thanks.
Thanks
All
so
right.
much. And would you like to finish up on this slide, or is this a good stopping point for you?
No, if you have another question, I'm happy to take it. I'm just concerned that I might be eating into time for the subsequent.
Yeah. So this is great. I mean, that's wonderful. Thank you very much. That was very interesting. I think it'd be great, and this is a great segue into the Weaveworks and how this is actually being deployed in the real world. So I don't know, Richard and Chris, I'll turn it over to you guys. I'm not sure.
So I will say a couple of things before I transition over.
Sure.
And my apologies. The first one is that with Firecracker, we're sort of looking to integrate with the rest of the container, as well as sort of broader ecosystem around GitOps and DevOps, etc. And we have a number of integrations in place. We support Linux and OSP guests. We support ARM now. We support Containerd. Firecube is essentially a Weaveworks offering that sort of is like a distribution around Firecracker, with the rest of sort of Weaveworks' opinionated workflows around GitOps. We also have BottleRocket, which is an AWS OS, a Linux distribution purpose-built for containers, where we're, one of the things we have in our roadmap is the ability to integrate that with Firecracker, thereby providing micro VM isolation as opposed to C groups and namespace isolation. I'll leave you with one last thought before I transition over, which is that Firecracker is an open source project, and sort of the roadmap is open, the code is open, and there's a lot of external collaboration that's happening as we speak. We also have a subsidiary sister project called Rust VMM in collaboration with folks from Red Hat, Intel, etc., where parts of Firecracker have been sort of made into building blocks to build your own VMM, and Rust VMM is a core part of that. In terms of opportunities for, and we really encourage folks to participate in sort of the Firecracker open source project in any capacity. Some of the big opportunities that we have is in terms of IO performance. That's one of the things that we went over. The other big opportunity that we have is in terms of snapshots. So Firecracker launches are fast. We're looking to make it even faster by essentially allowing for the ability to take a snapshot of a running micro VM that is pre-initialized, and then restore from that snapshot, which would be almost an order of magnitude faster than a cold micro VM launch, which itself is fast when you compare it to VMs. So we have lots of opportunities here, and we look forward to collaborating via the open source project. And thank you for the opportunity. I'll transition over to our friends from Weave who have a higher level use case with Firecracker.
Thank you so much. This is great.
Cool. And so Martha, maybe you could put some links into some of the projects where they can, some of the areas where they might be able to contribute.
Certainly. I will do so in just a little bit.
Okay, cool. Thank you. That was great.
Excellent. So now we're going to see Firecracker at work in a demo. So Richard or Chris, feel free to take it away.
Sure. Yeah, I'll kick this off. I'm just pulling everything up. You can see my screen okay?
Yes, it's great.
So yeah, that was a wonderful intro. Thanks very much, Samartha. I really appreciate the nuances of Firecracker being explained ahead of anything that we have to say. I'm Chris Lavery, and my colleague Richard is presenting alongside me. And yeah, let's kick this off. Try and leave as much time for questions as needed. So yeah, Richard, if you'd like to introduce yourself, feel free.
I can leave it for later, don't worry.
On your behalf. So yeah, Richard's the tech lead for Liquid Metal. He's also the maintainer of the cluster API provider for AWS called Kappa. And I'm a consulting reliability engineer currently working with Deutsche Telekom on their Shift platform. We both work at Weaveworks, the GitOps company. We're Kubernetes enthusiasts and experienced practitioners in the space. Let's see. I'll take slides 4 to 12. Yeah, and we'll bridge over to Richard afterwards. So yeah, like all good open source projects, Liquid Metal's inception was underwritten by our long-standing and open source embracing customer, Deutsche Telekom, or DT as they're abbreviated to in familiar circles. So DT are one of the largest network operators in the world, providing voice and data services to large segments of the EU and the US through subsidiaries such as T-Mobile. They're also incredibly savvy and well-learned on-premise operators. They bring with them all of the very deepest and darkest interesting caveats of running your own private cloud and your own network. So yeah, in conjunction with Weaveworks, they're leveraging the power of GitOps to deliver a cloud-native platform which can realize a vision of modern, scalable compute built on top of Kubernetes. The Kubernetes team envisioned delivering the same developer experience across different compute scenarios. From those, they are already running legacy software and services in their existing core sites. To those that are running it at the edge, where the clusters may be smaller and where compute resource is constrained by smaller facilities, and right down to the far edge where they need to reduce round trip response times, and where those response times are most they have the highest, let me think about this, where they matter the most, where they have the most significant impact on the customer use cases and specialisms. And 5G is a primary driver in this area. So private factory, Internet of Things, autonomous vehicles, they all utilize high bandwidth. They would all prefer low latency connections, and their applications have stringent requirements. So on top of these concerns, the heterogeneous infrastructure require the orchestration layers decoupled from the infrastructure provider through the most simple means of abstraction. In this case, the rule of simple does not mean easy, as orchestration needs to provide a consistent experience for the operator, but also an accommodating and pluggable format for the infrastructure provider. So there are instances where applications may even need to lease hardware, but their cluster control plane would take no benefit in consuming these resources. So optimizing towards cluster profiles, which are discrete and highly specialized. And that's on top of the already significant complexity in running like different infrastructure as a service topologies. So the scale of the platform requires all this complexity to be managed elegantly. It needs to be instrumented consistently, and it needs to be accommodating of geographical diversity and maintain reliability and availability, SLAs and SLOs in line with industry regulations. The preference is to manage clusters through GitOps so that homogeneous traits can be lifecycle managed in a scalable fashion, where they are application, platform, or infrastructure components. So very much a case of running many clusters in as consistent and repeatable, reproducible manner as possible. So to dig into what that means when we decided to build a cloud native engine for these clusters and call it Shift. Das Schiff is the ship in German, and it is the ship on which we sail. It is the ship on which we journey. So it
Very
very
cool.
much is. Yeah, we thought so too. It's very much indicative of like acknowledging that this is both a cloud native transformation, and it is also a platform, and it's things that are happening in parallel but continuously within the team and on behalf of their customers. So like they've ascribed a certain amount of principles that they feel would be ideals, but like things that they're working and we're working towards with them to create the shift in its fullest form. So like 100% upstream Kubernetes without additional complications. The platform should comprise of an open modular set of components which will work together in principles established through cloud native and implemented through the design patterns of Kubernetes. 100% standalone functioning of the clusters. The clusters need to be reliable in the face of any issue which would impact the availability of their orchestrator or control plane. They minimize downtime, and being able to perform service upgrades irrespective of the application workloads is a necessity. 100% infrastructure agnostic, that it supports multiple infrastructure stacks. That would be they're decoupled from the infrastructure underneath, but also capable of accommodating both existing and future infrastructure providers. It's 100% declarative. So declare the desired state, and so it shall be realized through a common reconciliation process. In this case, driven by the Kubernetes and/or cluster API and orchestrated by Weaveworks Flux, handling both infrastructure and application reconciliation and ensuring declarations of all components. It's 100% immutable on an OS level. So we cannot afford nor should need to manage aspects of the kernel or the root file system or any associated packaging at runtime. Images are built and updated as needed, and nodes will be rotated and redeployed as necessary. And 100% GitOps managed and automated. State is driven from numerous source code repositories and backed on privately hosted the Deutsche Telekom Git service with a combination of CI and automation. And we're able to manage the build, test, and release management process to ensure maximum coverage of the platform as code. So with all that stated, we should take a look at the hardware on which this platform will live. So this hardware is what we are deploying going forwards, but there is also a mix of other vendor hardware on which we have deployed that shift already. This is the next gen, but it is really current gen. We have it in lab, and it's all whirring and going and being warm. So the hardware selection extends the platform principles through to the hardware itself, and the Ywin EP100 chassis was selected for its minimal footprint and OCP compatibility, and which is the Open Compute platform, which is a kind of standard or an initiative that is driving towards better interoperable standards within the data center on which we can build compute from the hardware perspective. And the preference for that specific chassis is resource density and power efficiency to maximize the complete value of the edge. So micro VMs, both Kubernetes masters and Kubernetes workers, could run on each of the nodes on each of the 3 designated nodes for the UVMs. That's how we internally are referencing or abbreviating micro virtual machine. And due to the hardware isolation of a virtualized cluster, tenants can be co-located without contending for resource or complicating access controls. So the design allows for a minimum of highly available physical nodes to support an odd number of masters or workers. They could be even workers, for instance, but ideally, certainly in the masters, you'd want them to be odd for things like, in the event of a network partition, you'll want a minority majority leader election topology, and you'll also want to be able to potentially have backup and understand the failure domain, like how it responds in a way that's let's say standard or best practice as described by Kubernetes. themselves, well, I say Kubernetes themselves, by the SIG steering group that oversee Kubernetes as a project. So in addition to that, we have a single bare metal node, which is there to provide specific hardware needs for applications which need to patch in a node and utilize underlying hardware or hardware related functionality, such as SRIOV or DPDK or anything specifically, as obviously Deutsche Telekom do have and will have functions pertaining to the network, and certainly applications that are voice or data centric. The network's an incredibly important part, and that's why we have a bare metal machine there.
Chris, can I just jump in and just ask a quick question out of curiosity? Just very quickly, so how long was the process of how long did it take you to sort of settle on this hardware configuration? Was that something you were using before? Or
so I lost the last 3 seconds of your.
Oh, I was just going to say, was it something that you had used, that you were thinking about before, or was it something that you had built out all of your requirements and then went searching the right?
I think the requirements were always before any kind of discovery, but there's also been, there's been consideration and reconsideration, and the preference, for instance, that we haven't maybe fleshed out as much of this as we could, but for the sake of fitting everything into today's talk, like for instance, single socket servers were immediately shoot down quite a few options. Then just I think the fundamentals of when Wywin advertises this being open edge compliant, this is a completely different chassis format, the OCP chassis format. This is almost 50%. This isn't like a full long length physical host. This is like a half stack. So you can fit these in and potentially fit in a much more condensed HVAC system, a much simpler topology. When we say these will be running in the edge and far edge, we're talking about potentially even just a single one of these being deployed right beside a cell tower, where there is, there's maybe not even a full 42 rack. So like that instantly shoots down quite a number of things. And whilst other interesting topologies have been considered, and we do have hardware in lab that would not necessarily be this, this is form factor is certainly a driving proponent of why this is the front runner. And what the preferences are. I think it idealizes or epitomizes the preferences certainly for 5G and edge operators.
Got it. That's great. Thank you.
Cool, no problem. Also included is a hotspur, which any of the other workloads, either the virtualized micro VM workloads or the bare metal, could be deployed upon, so we can flip over in the event of failure. And with the business case and the platform principles out of the way, it's time to explain the specifics of liquid metal and how it succeeds in meeting the needs of tomorrow's edge platform. So cue Richard. Happy to stop sharing.
Perfect.
If you're ready to share.
Thanks very much, Chris. That's great.
Cool. Thanks, Chris. Give us 2 seconds. Hopefully you can all see that. Obviously, if I'm running out of time, feel free to give me a nudge to speed up.
Sure. I mean, and just for that, I think let's take 10 minutes or so on this, and that would keep us on track.
Yeah. Cool.
Excellent.
Brilliant. So Liquid Metal is fundamentally a code name. So it's not an actual product. It is really a code name for a set of products that we are actually building that all come together to deliver this vision for DT. So at a high level, the goal is actually to provision Kubernetes clusters that are made up of Firecracker micro VMs, and then optionally include whole bare metal nodes into that cluster. Cluster creation needs to be dynamic and aware of its operating environment. So what I mean by this is when we request a micro VM-based cluster is created, it should dynamically determine the optimum placement of the micro VMs on the available pool of bare metal hosts. And as you can imagine, there's many factors that come into play here. So a bit like scheduling a pod in Kubernetes, what are the resource requirements for these micro VMs? How many am I creating? How many hosts, bare metal hosts do I have? What is the utilization of those hosts already? Is there any affinity and toleration? So all of those things that we see with scheduling pods apply to micro VMs on bare metal hosts. And then we get to also another aspect that Chris alluded to is that not everything can be virtualized. So that might be for technical reasons, or it might just be for plain licensing reasons. So there is this requirement that we support adding a whole bare metal node. So in that diagram that Chris just, or the example hardware that Chris just showed, so one of those hosts will be joined as a whole Kubernetes node to a virtualized cluster. And this is what we call mixed mode. And then going back to the DT principles that Chris just covered, and the fact that we are the GitOps company, we decided early on that the cluster provision and lifecycle management must be declarative. And this is mainly to make it GitOps friendly. And that requirement sort of pushed us down the route of cluster API, and I will talk about cluster API later on. But we are early adopters and huge advocates of cluster API. So the projects that make up the Liquid Metal will be mostly open source. We are a commercial company, so there may be aspects that will be closed source, but the vast majority will as a lot of Weave stuff here, will be open source. And there will be contracts. So if you want to write your own scheduler, as long as you adhere to the proto schema, you can just plug that in and it should work. But it'd be very easy for us to build something that's completely bespoke to this one customer. We are treating this like a product, so that it is generally applicable to other telcos and other companies that want to create virtualized clusters in the most efficient way. So, sorry.
Richard, just out of curiosity, so that's an interesting point about telcos. It's not just for telcos, no. Right? Like this could be, it's basically anyone running clusters on bare metal.
Yeah, exactly. Okay. Yeah, and we are targeting Kubernetes only here. So,
right.
You could get a more generalized virtualization solution. There's plenty out there, open source and commercial, but this is purely for creating virtualized Kubernetes clusters in the most efficient way, right, on bare metal machines. But yeah, we've talked to some big technology companies. They have data centers still. They're always going to have data centers, yep. and it's it suits anyone in that type of environment.
That's right. And do you think you're getting an interesting inside look with the telcos and the sort of the edge requirements? Are you seeing any other industries that have that same sort of need?
Yeah, it's really interesting since we've been doing this. We've talked to give an example, a medical devices company. Essentially, they run virtual machines in their MRI scanners. So they currently use a well-known virtualization solution, but they want something that is a bit more cost effective, but is less resource intensive. And so the fact that something like this could be run in an MRI scanner is pretty interesting. And then there's just the bog standard. I want to run more on the same bit of tin.
Right. Yeah. Right. Very interesting. Very interesting. And just for clarity, is this something that people can already start to contribute to and use?
So I'm going to say it's early days. So there's going to be 3 projects. So we started on the main part. I'll cover that in a minute, which is called Flintlock. That does all the interaction with Firecracker and Containerd and stuff like that. So that is a lot further down the road, and that you can use that. We've done our first alpha release, and we would like contributors to that. And then we've just started on the second project, which is the orchestration part, so the cluster API part of it.
Great.
But that's a nice segue to this question that has come up already. Is we already have Ignite, we already have Firecube, and now we've got this liquid metal thing. So which one am I supposed to use? What's the difference and stuff like that. So just to give history, Ignite was the first project that we used Firecracker with, and it was really designed to bring a Docker CLI experience to creating and running micro VMs. So it was very focused on that CLI experience, and it brought the use of instead of having to create raw file systems, you could use a container, and it is very much the inspiration for the work that we're doing. And actually, Flintlock was originally called Reignite, just to show its lineage, but it caused some confusion. And then we have this thing called Firecube. And this was essentially a proof of concept to say, well, given that I've got these micro VMs created by Ignite, can I create a Kubernetes cluster out of them? And yes, you can. And both these projects were started as essentially summer projects for interns, but they were very, very early on in I guess Firecracker's life after it had been open sourced. So they proved a lot, and basically the Liquid Metal owes its inception and what we're doing to those two projects. So I think of it as the evolution of those two. And I guess the main difference here is Liquid Metal is designed to be completely declarative and API driven. There's no CLI focus at the moment. It's not designed to be a proof of concept. It's going to be actually designed for production use by DT, by this telco, and it's going to be driven by I guess the community direction with provisioning Kubernetes clusters, which is essentially cluster API. And then the interesting part is to be environmentally aware and to react dynamically to this bare metal environment. We have to then integrate with some bare metal provisioners and provide that integration part, which is really quite interesting. I won't go into the scenarios because I think Chris covered those.
And Richard, very quickly, there was a question that came in. Are there docs or a README somewhere that people can check out? And if so, could you post a link?
Yeah, I'll post a link. After I finished, definitely. I won't go into the scenarios, but when you look at the slides, it's just again confirming what Chris talked about, having fully virtualized clusters and then a part virtual and physical cluster to meet the needs of the telco. So just going to what we're building. So I've mentioned cluster API quite a few times. So for those people that don't know what cluster API is, it's basically bringing the same declarative Kubernetes style API to cluster creation like you do for the workloads that run in a Kubernetes cluster. So I can declare a cluster of 5 nodes, put that into a management cluster, and then CAPI and its various providers will understand that declaration and then go out and provision the infrastructure that is required for that cluster, and then bootstrap Kubernetes on top of that. So it's a way of providing this single operating model and cluster creation and lifecycle management across multiple infrastructure providers. And then there are an increasing number of cluster API infrastructure providers. So, AWS, all the big clouds, but then people like Tinkerbell are building their own ones. So you can actually bootstrap a physical Kubernetes cluster via declaration, and it does all the interaction with Tinkerbell. As I mentioned,
and Richard, sorry to interrupt. There's just a sort of a question here: is there a Liquid Metal provider for cluster API now, or is it planned? It's a good question for the slide.
Yeah. So we're developing it. Yep. So we're calling it cluster API provider micro VM. So at the bottom there, cap MVM. Everything seems to be prefixed with cap. But yeah. So we started that. It's currently closed source. but we will be open sourcing it when there is actually something there that people can use. But yeah, it's along the way. So just to give a picture of how this all fits together along the way. So when we talk about this, we talk about two locations. We have a management location that manages a number of edge locations or a number of clusters at an edge location. So that all starts with a bare metal provisioner. We use Tinkerbell internally for this, because it's really quite nice to use. But essentially, you'll plug in one of those. The hardware that Chris showed will be a physical host. Tinkerbell comes along and provisions a base operating system onto that host, and it will stick on sort of the requirements, the prerequisites for us to run our stuff. So there's two main things that we require. One is Firecracker, and the other one is Containerd. And so Flintlock is the first of the components of Liquid Metal, and this is the thing that does all the interaction with Containerd, does all the interaction with Firecracker, and it knows how to start micro VMs essentially. But at this point, we've just got a bunch of physical hosts with some stuff on it. They're not doing anything. Now, Flintlock exposes a API that you can call to essentially create and delete micro VMs and query the state of micro VMs. And that's what we will use later on. But essentially, these hosts are sat there doing nothing. So then this is where the management location comes in, and this is where the CAPI, the cluster API concept of a management cluster comes in. So if we want a micro VM based cluster, we write the YAML for it. Say, hey, we want a cluster with 5 micro VM, five micro VM based nodes, and we apply that to the management cluster. So now going back to that question, this is where the new CAPI provider comes in. So it understands that definition and goes, oh, okay, yeah, you want this micro VM based cluster. So there's two ways we can then do that. You could explicitly say where you want each of the Kubernetes nodes on which physical host you want to place them on. So we call that static placement. Which, it's not dynamic in any way. So that's okay. But the best way is to have this dynamic placement of the micro VMs onto that pool of physical machines on the right hand side. So the cluster API provider will actually call the scheduler and say, hey, I need to create 5 micro VMs. These are the specs of the micro VMs. So please, can you tell me on what physical machines I should to create those on? And it has to actually talk to the bare metal provisioner. I'm not saying that'll be synchronous. We are thinking more it'll be an asynchronous call there to get that inventory of bare metal hosts, and then it will need to query obviously the existing usage on the bare metal host, number of micro VMs running, et cetera. But essentially, it's going to say, right, place this micro VM on this host. So we've got that now, and then we're going to talk to the rest of the cluster API components. Now there's multiple ones of these. The interesting ones here are the bootstrap components. So there is a kubeadm bootstrap component that essentially will generate the kubeadm config as a cloud init. So we will cloud init configuration. So we take that cloud init configuration along with the spec, and then we call Flintlock to say, hey, create me this micro VM with this spec and this cloud init configuration. The Flintlock gets the container images. So with Liquid Metal and Flintlock, you don't have to worry about raw file systems. You say what volumes and kernel and RAM disk you want to use via container images. So it will pull those down and snapshot them and present those as block devices for Firecracker. And then it will call Firecracker and say, hey, start me a micro VM. Firecracker does that, and because we have because we're using Cloud Init, which contains kubeadm, that then bootstraps Kubernetes within that micro VM. So the point here is that a micro VM in this instance is a whole Kubernetes node. It's not representing a pod; it's representing a whole node. So you then combine these micro VMs into a cluster across multiple physical hosts. That's basically what we're building. So we did a proof of concept with Firecracker and Kubernetes clusters. We actually created them as EKSD clusters, so a particular variation of Kubernetes. We used a new feature that is going to be released next year in Firecracker to support Mac VTAP network interfaces, but we proved it out, and then now we're building Flintlock and the CAPI provider. There is an alpha release of Flintlock, so you can download it. As it is an alpha, you may encounter problems, but feel free to try it. So I won't go into this, but one thing I will say is that there's two parts. There's the API and the reconciliation, the thing that does creates the micro VMs, and we are heavily reliant on containerd here. We use it for all of the container image stuff, snapshotting, mounting of the container images. We use the content store to store the micro VM, and we use the event service. So we're heavily reliant on it to the point that we might have a deployment option where containerd and Flintlock are combined as one binary. So have I got time for a demo? What we have?
I think a demo would be great.
Yep, cool. So we don't have the cluster API provider, but I will let's see how this goes. Hopefully the demo gods will be good.
The demo gods are never friendly.
No. So so on screen you should see Bloom RPC. So it's just a UI to make a gRPC request. So this is basically going to make a gRPC request to Flintlock to say create a micro VM. So a couple of things to note is, you give the specification of the micro VM. So numbers, virtual CPUs, the number of the amount of memory, but then you can see that we're actually using a container image for the kernel. So you package your kernel up as a container image. You don't have to copy the kernel around, and then there's any command line arguments to the kernel. And the interesting thing here, from a Firecracker point of view, is Firecracker has a built-in metadata service, so you can actually use that as a data source for Cloud Init. So you can pre-populate the metadata service for that Firecracker instance, and then use that for Cloud Init later on. So that's why that's up there on the end. And that's the same for RAM disks and volumes. Again, they all come from container images. And then you can specify the network interfaces. So at the moment we support TAP and Mac VTAP interfaces, and there's various configuration options there. And then right at the bottom there is, this is the detail that we're going to push into the metadata service. So the idea is that you send that into, hopefully this will show. Let me just change that, because that would have failed. So if I send that in, hopefully nothing's happened.
It's the demo gods.
It's not because sorry, I hadn't put my password in. So what you should be seeing on the screen now behind is the virtual machine start. So it's pretty quick. I will say the slowness to actually configuring Firecracker and telling the micro VM to start is about 500 milliseconds on my desktop machine here. And then this is just an Ubuntu cloud image that is booted here. We haven't done any optimization there, so there is some time that it's waiting to get a DHCP address. We are doing some we're doing an app to update and an app to install as part of that boot process. But you can see, essentially, you can see that the micro VM has already started. And if I want, I can I can SSH onto that. Fine. That's all good. I don't have the cluster API provider. So the way that I'm going to create a Kubernetes cluster out of this micro VM is I'm going to use something called K3S up. So K3S up is an open source tool that will install K3S via SSH. So if I do this, so I can use K3S up to say on this host, which is called MVM, using this user and this key, install K3s and create a Kubernetes cluster. So that should go away now, and that will install Kubernetes onto that micro VM. So while that is doing that, it shouldn't take too long. Actually, I might as well wait for it. It does take on the first node where it's actually going to cluster. It does take a little bit longer, but essentially that will hopefully come up. Ooh. There we go. Cool. So yeah, so we should see that is running. Yeah, so the node is ready. So that's fairly interesting. Oh no. Have I just killed my machine? Oh no. Uh-oh. I might have to restart.
Sure.
That.
Yeah. And I think, I'd like to get back, like, while you're restarting that, some questions came up that I think maybe we could just go through a little bit. So Venkat asked the question, he said, what's the qualifying criteria, minimum requirements for integration with bare metal provisioners? You talked a little bit about that at the beginning, but is there sort of a hard criteria there?
No. So,
okay.
So there's going to be two ways we're going to do that. So we're going to obviously have to support some out of the box because we need to use some for our own testing. Just so that we've chosen Tinkerbell because we like it. But there's going to be two ways that if you don't use Tinkerbell, and we will add more additional support as we go on. So we're going to provide a contract essentially. So if you write a service that adheres to that contract and return your available pool of bare metal nodes in via that service, we can call it. So that's one way. And the secondary way is there will be custom resources that you can apply to the management cluster, and we will look at those as well. So you can push those custom resources that tells us about a specific node, or we can call a service.
Great. Let's go to questions. There were some questions, and actually, I think Venkat, you very patiently sort of waited. You had some questions at the beginning. Would you like to ask those now? And anyone else who has questions, I think this is a great time to sort of jump into Q&A.
I just let Venkat talk.
Great.
Hey, Venkat,
that's great.
Are you there?
Yes, very much.
Cool. We like to hear your voice, Venkat. We like to hear your voice.
So nice of you. So nice of you. It's quite motivating at the midnight past 46 minutes. So these are some of the things for Chris, what are the most three challenging complexities that they have encountered while considering the use case, what was shared with us? Because it was quite enlightening and interesting, because Deutsche Telekom is a known telecom provider of the world. And certainly, if he could shed some light and enlighten us with respect to some of the challenging complexities that can really help us. That is one thing. And another thing, because as I've been associated with 9X and Bell Labs in the past, the operational efficiency is the sort of the most important factor to consider, and what's that's been accomplished at the at the time of planning or inception. Chris can throw some light. I know, it'll be a great thing. Otherwise, later also you can share it or through Josh.
Sure. So I'll try and pick up. I mean, these will be opinionated and probably.
We love opinions. We love opinions. Strong opinions.
Yes.
Bring it.
I try and tone mine down instead of chew them up. But Yes, I think that what instantly hit me was that a tier 1 network operator brings with it all of the true complexity of running services that exhibit qualities that straddle both the cloud native aspiration and also the existing legacy software like topologies that have been used for traditional services. So like there are things that, for instance, there is no NATed IP inside the Kubernetes environment that we run. Like all pods are routable. So that brings with it, if you can imagine, if you like applying a multi-tenant hard isolation model inside an operator who requires that to be enforced down to the network layer. Like there's an incredible amount of IP address management, rule-based control, granular policing and leasing of IPs, and we've had to use, you know, and adopt services, external services to Kubernetes to be able to manage IPAM and write bespoke code to specifically deal with those aspects as an operator. So that's something that, like, for instance, you rely on heavily and is abstracted away from you when you are using AWS. You don't think about having to do that. You don't think about, for instance, a legacy application having to maintain a heartbeat where two MAC addresses are effectively connected by like a link tunnel. Like to those MAC addresses that are peering and heartbeating one another, they don't know that there is, like, that they're going into a VXLAN tunnel, that the VXLAN is being carried over a cloth fabric, that actually terminates on an adjoining worker node, that the worker node has an interface which decapsulates, that the decapsulated MAC address is then a part of an interface that is specifically accessible by a discrete pod or pods. So when you bring the edge and the existing workloads together, you're having to solve both those problems in one common platform. So that'll be like a good technical exercise, a good example. On the operational side of things, I think like the team set out with the goal and the desire to make this as observable, as performant, as clean to operate through a process as possible. And the Dash Shift engineering team have been, like, they've been exceptional and at bringing ideas to the table, at ascertaining where the breakpoints are for them with regards to pushing out clusters, making changes to clusters, making upgrades to clusters, wanting to do so at a fleet level, being able and capable of managing different segments of compute and different segments of like geographical disparity, like being able to make changes at, you know, as dry and clean as possible and visible as possible. And to do that, they chose GitOps, and they reached out to us as the experts in the field, and we've set about creating a pretty comprehensive, a pretty great design with their vision and our input. And it really is like that way around, that they see everything from the specifics of their hierarchy, their deployment, and we apply our architectural understanding and learning to that. So that would be another one. And I think of another challenging complexity.
I can assist you with the third one, if it is okay. It's the sort of SLA incremental efficiency that could be one of the operational things. You know, if you had an opportunity to have an idea about that, maybe.
You mean what kind of SLAs they're upholding, or how they're devising SLAs or SLOs, or?
improvement that resulted.
Maybe
And you a baseline, and then how we
Yes.
and then
yes,
how we reached.
absolutely, Chris. So yes.
I'm trying to think of what is the best example. Yeah.
Oh, sorry.
Chris, while you think about that, let's just go back to Richard for a sec. If
yes.
give him
yes.
give him a chance to sort of wrap up where he was, and then I think just in the interest of time,
Yes.
we'll go to if there's sort of some remaining questions, we'll do that, and then we'll finish up.
Thank you.
That works for everyone.
Thank you.
Yeah.
Thank you.
Thank
Richard,
you.
maybe just summarize, Richard, what you were going to cover.
Yep. Cool. Yeah. So actually, it didn't die in the end. I just opened Windows. But really, the only thing I was going to cover was I was going to start a second micro VM, and then add that to the already existing Kubernetes node. So we didn't miss too much, and then I was just going to show how we use containerd. But yeah, just to summarize and recap, so Liquid Metal is made up of 3 main projects. So there's Flintlock, which you saw today, and that is open source and available at that location. There is a cluster API provided micro VM that's recently started. So we started defining the API types and the reconcilers for that, and the scheduler is to be started. So heavily reliant on cluster API, like I've said before, and it supports the fully virtualized and mixed mode clusters. And the main thing here is as this is all open source, contributions are really welcome in whatever form they are, whether that's code, whether that's testing, whatever that is, and just general input in the direction of this product. And there is now for release. If you're feeling, I was gonna say risky, that's probably the wrong word, but go ahead and play with it and just see what you think with it. But yeah, and one question did come up, and I know Chris has answered that, is so Ignite and Firecube will still be supported. Ignite definitely, because that's a very different use case. That is, I'm on the command line, and I want to replicate that experience. Whereas this is, a more focused use case on purely creating Kubernetes clusters. So hopefully that recaps. Great,
that was wonderful, and I think that's perfect. There's one question from Malcolm to either of you. How are you solving networking between the micro VMs enough to get 3x Kubernetes control plane micro VMs to talk across 3 of those blades? So
yeah, was that Chris or Slow?
I mean, I think it's probably more specific to you. I can answer how those things work inside a telecoms or edge environment generically, but I think it might be deeper than that.
Yeah.
Okay.
So,
it's a very good question. Maybe there's a way to that we can answer that offline. Again, I'm cognizant of the time, and I want to. I think now is probably a good time to wrap things up.
I was just going to say on that point.
There you go.
Yeah, the Firecracker team added a feature to Firecracker that's going to be released next year, and essentially that adds support for Mac VTAP to Firecracker. So we can essentially create a sub network interface on the host for usage by that micro VM only, and that's how we're doing it. So obviously there's intricacies in how you wire your actual network, but it does present the micro VM to the network directly. So that's just
cool.
Just as a quick summary.
Excellent. Thank you so much. This has been a wonderful event. I think that I just want to take a moment to thank Zellersoft and Vasu and Josh and the people that went into putting this together, as well as the Weaveworks folks for the sponsorship. The Cloud Native group, Cloud Native at Scale, is wonderful to be a part of, and I want to thank everyone. Samartha, for your participation and presentation. It was really, really good. And really thanks to everyone for taking the time today to join us. These are always, I I always walk away, having learned a lot, met some interesting people, and great to have everyone together.
Awesome. Thank you, everybody. I put the next event in the chat there, so please join us. For those of you who don't know, Tracy, so I saw her at the QCon conference in LA a couple of weeks ago. She was she did a lightning talk at GitOpsCon. She's fantastic. If you haven't heard her speak, I highly, highly recommend coming if you're interested in this topic, taming microservices through an evolved DevOps pipeline. And so the link, will take you to our meetup there, and we'll be pushing that out starting tomorrow. We'll send the recorded video tomorrow as well, along with the presentations. So to our speakers, Rich, Chris, and Samantha, please send me your presentations and I'll push that out to the world, to our audience. And yeah, thanks everybody. Really, really appreciate it. And we will be seeing you soon. Take care, guys. Bye.
Bye, everyone.
Cheers, folks.